Dear students, so in this video, we'll study the valence bond theory for the compounds with coordination number 6. Now, when it comes to the compound with coordination number 6, there are two types of hybridization possible. That is D2 sp3 and sp3 D2. Now, D2sp3 hybridization will use 2d orbitals from 3d subcell. Remember, if it is on the left hand side, the d orbitals will come from 3d. But if it is on the right hand side, the d orbitals will come from 4d. Next, now how will you know whether to use D2sp3 or sp3d2? Very simple. Check the nature of the ligand. Means whether the ligand is strong filled or weak filled. So if the ligand is strong filled ligand, we'll use D2sp3. If it is weak filled ligand, we'll use sp3d2. So let us discuss this with the help of example. So the first example which I'm going to take is CrNH3 charge 3 positive. So first you write down the electronic configuration of chromium. So chromium atomic number is 24. Electronic configuration is argon, 3d5, 4s1, 4p0, 4d0. Next, you calculate the oxidation number. Let the oxidation number of chromium be X plus NH3 is a neutral ligand, so charge is 0 multiplied by 6 is equal to plus 3. So the oxidation number of chromium in this compound is 3 positive. So the electronic configuration for chromium 3 positive. Number of electrons will be 21. The electronic configuration will be argon. We'll remove 1 from 4s and 2 from 3d, since we have to remove total 3 electrons. So it will be 3d3, 4s0, 4p0, 4d0. Now, you know NH3 is strong filled ligand. So it will use D2sp3 hybridization. That means the 2d orbitals will come from 3d subcell. That means for this compound, we don't need to use 4d subcell. So let us draw the orbitals. So in 3d, we have 5 orbitals, 4s, 1, 4p, 3. In 3d, you have 3 electrons, so 1, 2, 3, 4s, 0, 4p, 0. Now, the hybridization is D2sp3. So, we need 2d orbitals from 3d. Now, you can see we already have vacant orbitals in 3d. You already have 2 vacant orbitals in 3d. So, we don't need to force pairing. But in case, if we don't have vacant d orbital, and if it is a strong fill ligand, we'll have to force pairing. So in this compound, we already have vacant d orbital. We need 2, so 1, 2. We need 1s, 3. We need 3p, 4, 5, 6. So total 6 hybridized orbitals will be formed. So from 3d we have used 2 orbitals for hybridization, so there will be 3 left. Hybridization is D2sp3. And each vacant hybridized orbital will be occupied by the pair of electrons donated by NH3. So NH3, pair of electron, So this is the valence bond approach for a compound with coordination number 6, where the ligand is strong field ligand. Now, from here, if you're asked what is the hybridization of the compound, is D2sp3. Geometry, if it is D2sp3, geometry is octahedral. What is the magnetic property? Now you can see here we have unpaired electrons. So the magnetic property is paramagnetic. What is the magnetic moment of this compound? Mu is equal to root over n into n plus 2, where n is number of unpaired electrons. So you have 3 unpaired electrons, so n is equal to 3. So 3 into 3 plus 2, so it will be root over 15. Unit of magnetic moment is Bn. Now, for compounds with coordination number 6, you will be also asked the nature of the complex. That is, whether it's low spin complex or high spin complex. Now, in case the compound uses D2sp3, it is low spin complex. And if the compound uses sp3d2, the compound is high spin complex. So let us take an example where the compound uses sp3d2 hybridization. So this is a compound with coordination number 6 and weak field ligand. So again we start with the electronic configuration of the metal ion, that is cobalt. Atomic number is 27. So electronic configuration is argon, 3d7, 4s2, 4p0, 4d0. Next, calculate the oxidation number. So let the oxidation number of cobalt be x plus minus 1 multiplied by 6 is equal to minus 3. So x will be equal to plus 3. So the oxidation number of cobalt in this complex is plus 3. So the electronic configuration of cobalt 3 positive with 24 electrons is equal to argon 4s0, will remove 2 electrons from 4s and 1 from 3d. So it will be 3d6, 4p0, 4d0. Next, draw the orbitals. So 3d has got 5 orbitals, 4s1, 4p3. Now, it's a weak field ligand, so we'll use the hybridization sp3d2. That means the 2d orbitals will come from 4d subcell. So we have to draw the 4d orbitals also. Now, since it's a weak field ligand, cannot force pairing here, so we'll use 4d. So the hybridization will be 1s, 3p, and 2d. Hybridization is sp3d2, and the vacant orbitals or the empty orbitals is occupied by the pair of electrons donated by the ligand F negative. So you have 6 F negative, so you'll get 6 pair of electrons to form 6 coordinate bond, and you'll have 3 unhybridized 4d orbitals. So this is how we approach valence bond theory for coordination number 6 and having weak field ligand. Now, for this compound, the hybridization is sp3d2. Geometry. If it is sp3d2, the geometry is octahedral geometry. Next, what is the magnetic property? You can see we have unpaired electron here, 4 unpaired electrons, so it is paramagnetic. Magnetic moment you can calculate using the formula mu equal to root over n into n plus 2, where n is equal to 4. Now, whether it's a low spin or high spin, you check the hybridization. The hybridization is sp3d2. So it is a high spin complex. So you can compare, you can take more compounds, you try to find out the hybridization, geometry, and magnetic property. Now in case, if you have 2 compounds and you are asked to compare the paramagnetic character, okay? So you have 2 complexes or 2 compounds, you are asked to calculate the paramagnetic character. You do the valence bond approach. After that, you check the number of unpaired electrons. The compound having more number of unpaired electrons will be more paramagnetic in nature. So you can take more examples and practice yourself. So the next topic which we are going to study is crystal field theory.